Hello class, today we are starting chapter 7, Algebra, Graphs, Functions, and Linear Systems. We will be looking at chapter 7.1, Graphing and Functions. Our objectives today are to plot points in the rectangular coordinate system, graph equations in the rectangular coordinate system, use function notation, graph functions, use the vertical line test, and obtain information about a function from its graph. Points in ordered pairs are the first thing we will look at. The horizontal number line is your x-axis. The vertical number line is your y-axis in this coordinate plane. The point of intersection of these axes is their 0 point called the origin. Negative numbers are shown to the left of and below the origin. The axes divide the plane into 4 quarters called quadrants. So what we can see is the coordinate plane over here to our right hand side. We have our first quadrant, second quadrant, third quadrant, fourth quadrant. We have our origin here at 0, 0. We have our x-axis and our y-axis. Each point in the rectangular coordinate system corresponds to an ordered pair of real numbers, x, y. Look at the ordered pairs, -5, 3, and 3, -5. So, let's look at the first one, -5, 3. -5, 3, we travel left on the x-axis 5, and then we travel up 3. That's how we get to -5, 3. To get to 3, -5, we travel 3 on our x-axis and down 5 on our y-axis. The first number in each pair, called the x-coordinate, denotes the distance and direction from the origin along the x-axis. The second number in each pair, called the y-coordinate, denotes the vertical distance and direction along the x-axis or parallel to it. The figure shows how we plot or locate the points corresponding to the ordered pairs. So the first number is always your x. We move on our x first. And then your second number in your coordinate is your y. And we move accordingly to find the y point and then plot the point. We want to plot the points A, -3, 5. We'll do those one at a time. -3, 5. They're already plotted for you. We'll show you how you get there. -3, 5. We move left, -3, and then we move up 5. That's how we get to -3, 5. B is 2, -4. So we go right 2, down 4, and we're at 2, -4 for B. C is 5, 0. So we go 5 points to the right, and we don't go anywhere else. We go 0. So we put a point right there on the x-axis. D is -5, 3. So we move -5 points to the left. -3 means we go down 3 into quadrant 3 here. And we put a point right there for D. E is 0, 4. So we move nowhere on the x-axis, 0. And we go up 4 on the y-axis. And here's our E point. F is 0, 0. Means we go nowhere, and we're right here at our origin point. So, you can follow the solution of how we move from that origin point if you need to read below for further instruction, but I believe that's pretty explanatory. Graphs of equations. A relationship between two quantities can be expressed as an equation in two variables, such as y equals 4 minus x squared. A solution of an equation in two variables, x and y, is an ordered pair of real numbers with the following property. When the x-coordinate is substituted for x and the y-coordinate is substituted for y in the equation, we obtain a true statement. The graph of an equation of two variables is the set of all points whose coordinates satisfy the equation. So we want to look at graphing an equation using the point plotting method. We want to graph y equals 4 minus x squared. Select integers for x, starting with -3 and ending with 3. So, for each value of x, we find the corresponding value for y. We've got a nice chart here where we break it down. Our x values are pre-selected for us because we start with -3 and end with 3. This includes values of x equals -3, -2, -1, 0, 1, 2, 3. Okay, now our equation that we're dealing with here is y equals 4 minus x squared. What we want to do is take our x values here, plug them in for the highlighted red x here and simplify out to find our y value. Okay, so for x equals -3, the equation is 4 minus -3 squared equals 4 minus 9, that's just the simplification, equals -5. So our ordered pair overall is -3, comma, -5. We move on, -2. So we plug -2 in for x. We've got 4 minus -2 squared equals 4 minus 4 equals 0. So now we have the coordinate point -2, 0. For -1, I have y equals 4 minus -1 squared equals 4 minus 1, which is the same as 3. So our coordinate point here is -1, comma 3. Next, I plug in the 0 for x. Y equals 4 minus 0 squared equals 4 minus 0, which simplifies to 4. So we have the coordinate point 0, 4. Next, we have y equals 4 minus 1 squared equals 4 minus 1 equals 3. So we have the ordered pair 1, 3. We plug in the 2 for x next. 4 minus 2 squared equals 4 minus 4, which is 0. So we have the coordinate point 2, 0. Next, we do y equals 4 minus 3 squared, because we plug the 3 in for the x, which is the same as 4 minus 9, which simplifies to -5. So we have the ordered pair 3, -5. Takes some solving to do this by hand, but we get our ordered pairs that we need to plot in the end. So next, what we do is plot all of those ordered pairs. You can see this on the graph here. It says now plot these 7 points and join them with a smooth curve. This is exactly what we've done. We have the ordered pair -3, -5. So -3, -5 right here. We've got, this is the -3, -5 point that we found. We have the point -2, 0, -2, 0 right here. We have the point -1, 3, -1 up 3. That is right here. We have the point 0, 4, 0 up 4 right here. Next, we have the point 1, 3. So 1 up 3, 1, 3. It has been plotted. Next, we have the point 2, 0. So we go right 2, up 0. Have that point. And last but not least, we have the point 3, -5. We go over 3, down 5. You could see we have all these plotted points here, and then we just do as best we can with our pencil or pen to connect these points with a smooth curve. So let's look at functions. If an equation in two variables, x and y, yields precisely one value of y for each value of x, we say that y is a function of x. The notation y equals f of x indicates that the variable y is a function of x. The notation f of x is read f of x. Let's look at example 5, an application involving function notation. Tailgaters beware. If your car is going 35 miles per hour on dry pavement, your required stopping distance is 160 feet, or the distance the average person walks in 35 seconds. At 65 miles per hour, the distance required is 410 feet, or the distance the same person walks in a minute and a half. Figure A on the next slide shows stopping distances for cars at various speeds on dry roads and on wet roads. Figure B on the next slide uses a line graph to represent stopping distances at various speeds on dry roads. So let's look at this. We have our stopping distances for cars at selected speeds. We have a greenish color for dry pavement and a bluish color for wet pavement. Our stopping distance here is in feet. Our speed is in miles per hour. And obviously we could tell that when the pavement is wet, it requires a little bit further, no matter what the speed, to stop. Now if we look at our line graph over here, the stopping distances for cars on dry pavement, we can see it plotted out. Okay, and it is a curve going upward. The faster you go, the further it takes to stop. So, use the line graph to estimate a car's required stopping distance at 60 miles per hour on dry pavement. Round it to the nearest 10 feet. So, if we go back and look at this graph here, what we'll see is if we go to the graph at 60 and go up to where it hits the curve, right here at that point, what we see is when we carry it to the left to see where its corresponding y value would land, it lands at approximately 360 feet. So we can estimate that at 60 miles per hour, it's going to take us approximately 360 feet to stop on dry pavement. We've used this curve to estimate this distance. We know our speed. We see where it hits the graph. It's right there. And we take that and we correspond that over here to where it hits on the y-axis, which is our stopping distance. And we estimate it to the best of our ability. So, the required stopping distance at 60 miles per hour is estimated using the point below. The second coordinate of the point extends slightly more than midway between the 300 and the 400 on the vertical axis, thus 360 is a reasonable estimate. We conclude that at 60 miles per hour on dry pavement, the required stopping distance is approximately 360 feet. Let's look at B. B says the function f of x equals 0.0875 x squared minus 0.4x plus 66.6 models a car's required stopping distance f of x in feet on dry pavement traveling at x miles per hour. Use this function to find the required stopping distance at 60 miles per hour round to the nearest foot. What this means is we're now going to substitute this 60 miles per hour in for x. So we've visually done it on the graph and estimated. Now we're going to use the actual estimated function in order to find this. So we've got this function of x. F of x equals 0.0875 x squared minus 0.4x plus 66.6. And we're going to plug that 60 in. That's 60 miles per hour in for the x value. And that's what we do here. F of 60 equals 0.0875 times 60 squared minus 0.4 times 60 plus 66.6. Now we can use a calculator to simplify. And what we can see here is when we simplify these values, we get a value of 357.6, which is approximately 358 feet. This indicates that the required stopping distance on dry pavement at 60 miles per hour is approximately 358 feet. Now what we can tell is that our estimate back here, just using the graph of 360 feet, was reasonably close to what the equation gave us when we typed 60 in. We were only off by about 2 feet. Now example 6 of graphing functions says graph the functions f of x equals 2x and g of x equals 2x plus 4 in the same rectangular coordinate system. Select integers for x from -2 to 2 inclusive. For each function, we use tables to display the coordinates. So the coordinates in these functions below are garnered in this table. On the left, we have the f of x function, 2x, where we have gone from -2 to 2 on our x and found our corresponding coordinate points. On the right table, we have the g of x function, 2x plus 4, and we have found from x equals -2 up to x equals 2 the associated coordinate points here as well. Now, we can graph given those points that we have found on the previous page. It takes a little time to find all of these if you were to do this simply by hand on your own, but it is easily doable. All you're doing is plugging the x in for the x in the f of x function, finding the coordinated point. Same thing with the g function, plugging the x into the g function, simplifying so that you can find your coordinate point. Graphed, here's what these functions look like. If you also have a graphing calculator, you can simply graph these functions using your y equals on your graphing calculator. so that you compare them side by side. So here they are graphed. Our g of x function here, 2x plus 4, is in the red, while our f of x function, 2x, is in the blue. And what we can tell is that the g of x function compared to the f of x function has been shifted up 4 units. Do you see the relationship between the graph? And do you see how it shifted? So 2x is here, 2x plus 4 puts the graph 4 units up. So we had a vertical shift of the function. Now, one of the things we have to do when we start messing with these equations and graphing is we have to do the vertical line test for functions. If any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. Functions are very important, and following the function rule is very important. So, using the vertical line test, we want to identify graphs in which y is a function of x in example 7. So we're going to use this vertical line test. Now the vertical line test here just basically means that if I draw a vertical line anywhere, it should only ever hit at one point. So that was a terrible vertical line there. But if I draw a vertical line anywhere on the graph and it hits more than one point, then it's not a function. So A is not a function because here it hits the graph in several places at 2 points. On B, however, there's no vertical line that I can draw that hits it more than one point. So B is a function. C, if I draw a vertical line anywhere on C, it's only ever hitting at one point. I can't draw a vertical line that hits it more than one point. So it is also a function. D, I can draw a vertical line that hits more than one point, so it is not a function. What we can see here is just the solution, basically what we worked out on our own, that hey, for A, we have vertical lines that hit the graph twice. B, it is a function. C, it is a function. And D, it's not a function because we've got a vertical line that hits the graph at more than one point. Pretty easy. The vertical line test, I feel, is an easy test for function. About the easiest you can get. Now, example 8 says, analyzing the graph of a function. The given graph illustrates the body temperature from 8 a.m. through 3 p.m. Let x be the number of hours after 8 a.m. and y be the body temperature at time x. What is the temperature at 8 a.m.? Well, if this graph on the x-axis represents hours after 8 a.m., where did my cursor go? Oops, over here. Then, how many hours after 8 a.m. is 8 a.m.? Should just be 0 hours, right? At 0 hours, my body temperature is 101. During what period of time is your temperature decreasing? Well, decreasing means going down. So it looks like it starts going down right after 8 a.m. on down to 3 hours after 8 a.m. Well, what time is it 3 hours after 8 a.m.? 9, 10, 11. 11 a.m. So it looks like it's decreasing from 8 a.m. to 11 a.m. After that, it increases and then kind of steadies off and stays consistent. Now, C says estimate your minimum temperature during the time period shown. How many hours after 8 a.m. does this occur, and at what time does it occur? Okay. Our minimum temperature appears to be right here at this dot. And at that dot, it appears that it might be somewhere between 98 and 99. So let's take a best guess here that it might be, we'll say 98.7 degrees Fahrenheit. That's at 3 hours after 8 a.m. And at 3 hours after 8 a.m., that time is 11 a.m. Okay? Part D. During what period of time is your temperature increasing? Looks like we have an increase in temperature from 3 hours after 8 a.m. to 5 hours after 8 a.m. So 3 hours after 8 a.m. would be 11 a.m. and 5 hours after 8 a.m. should be 1 p.m. You can count it up with me if you want to. 8 a.m. to 9, 9 to 10, 10 to 11, 11 to 12, 12 to 1. That's 5 hours after 8 a.m. Part of the graph is shown as a horizontal line segment. What does this mean about your temperature, and when does this occur? Well, that horizontal line segment means that our temperature is consistent, right? So our temperature is consistent. And this occurs from 5 hours after 8 a.m. to 7 hours after 8 a.m. Well, 5 hours after 8 a.m. is 1 p.m., which means that 7 hours is 3 p.m. F says explain why the graph defines y as a function of x. The reason it defines y as a function of x is because no matter what vertical line I draw and where I draw it, it only ever hits one point. So it passes the vertical line test is a main reason that y is a function of x. Now, we can review these once again. The temperature, the solution for A, if you want to review it one more time typed up, some people have a hard time reading my handwriting. A says the temperature at 8 a.m. is when x equals 0, since no time has passed when it is 8 a.m. Thus, the temperature at 8 a.m. is 101 degrees Fahrenheit. The temperature is decreasing when the graph falls from left to right. This occurs between x equals 0 and x equals 3. Thus, the temperature is decreasing between the times of 8 a.m. and 11 a.m. The minimum temperature can be found by locating the lowest point on the graph. This point lies 3 above the horizontal axis. The y-coordinate falls midway between 98 and 99, approximately 98.6. We said 98.7. Close enough estimation there. Thus, the minimum temperature is 98.6 degrees Fahrenheit at 11 a.m. The temperature is increasing when the graph rises from left to right. This occurs between x equals 3 and x equals 5. Thus, the temperature is increasing from 11 a.m. to 1 p.m. The horizontal line segment shown indicates the temperature is neither increasing nor decreasing. The temperature remains the same at 100 degrees Fahrenheit between x equals 5 and x equals 7. Thus, the temperature is at a constant of 100 degrees Fahrenheit between 1 p.m. and 3 p.m. By the vertical line test, we can see that no vertical line will intersect the graph more than once, so the body temperature is a function of time. Each hour represents one body temperature. This is essentially everything we said and went through, just rehashed. This concludes the lecture. If you have any questions whatsoever, please don't hesitate to reach out and ask. I'm very reachable by email and will reply as soon as possible. I look forward to seeing you and lecturing you again for Chapter 7.2. Y'all have a good afternoon.